So before we, indict me for thinking machine learning automation is this terrible thing, I want to put this graphic up. This is what I did, a test I did when we rolled out BigML deep nets. You can see this is basically a whole bunch of classifiers in scikit-learn and R and Weka if you're a Java person. And I just wanted to make sure that BigML deep nets in general, depending on the data set and the metric, would beat all of these other things if you just pulled them off the shelf and used them, so with no parameter tuning. And so it does. So this is a good sanity check that we've developed something more than you can get just by going to the open source community. And a lot of the reason that BigML is winning over there is because of ML automation. So embedded in that deep net learning framework is things like automatically searching for network structure, using things like Bayesian parameter optimization, using the hyperband algorithm, using meta learning. All of that is embedded in our deep net framework. So I could talk about all that, like how we integrated that into the deep net framework, and like what were the most helpful things. But what fun would that be, right? I'd much rather talk about how broken machine learning automation is and why it's not a useful solution to a lot of problems. So let's do that instead. And basically, I'm going to talk about BigML first of all, and just if you don't know BigML, I'll give you a brief introduction, and then I'll talk about why essentially automation is the wrong thing for making machine learning more usable, and the way we should think about it is in terms of abstraction. So if you haven't ever seen BigML, the general idea of BigML is to make machine learning accessible to non-programmers. So we offer an API. If you want, you can make calls to our API. But we also have these kind of first-class visualizations of all of the different model types we create. And we do a variety of supervised and unsupervised models. And you can create them all with a kind of point-and-click interface. So you don't have to be a programmer to do machine learning on BigML. And of course, what we're always trying to do is limit the distance between the people who have data and a model in production, right? So part of the reason that we want to make it accessible to non-programmers is that's a barrier to entry, right? And so we're trying to eliminate all of these barriers to entry to get you from, oh, I'm a person who happens to have some data, to running a machine learning model. And so automation sounds like the right deal for us, right? Like, we don't want you to have to be an expert. Of course, we want to automate away all of the drudgery and technical detail associated with doing machine learning. So why am I saying in this talk that that's the wrong thing? Let's take a look. So to me, machine learning already looks pretty automated, right? Here's your data on this side. You plow it into this algorithm. A lot of even practitioners don't understand exactly what goes on in there, and out comes the model. So that's great, right? That's already a pretty automatic process. The distance between data and model is just that tiny box. But of course, that's wrong, right? Because in reality, it looks more like this. And in reality, it's even more complicated than this. But just as an example, this is the sort of thing that makes us consider automation, right? We have a pre-processing step for the data. That pre-processing step needs to be parameterized. The algorithm itself needs to be parameterized. Finally, after parameter tuning and various algorithmic selection and so on and so forth, you get the model. And so this seems like a good candidate for automation, right? A process like this. And so what most machine learning automation boils down to, the way it's pitched right now, is basically this, right? Basically, we just reblacken this box. So we just try to make it a box again that you plow data into and plow the model out. And that's fine as far as it goes. But it has all of the problems that the original process did, which is when people plow their data into this modeling process, they get the model out. They have no idea if it's a good model, whether or not they want to use it. You can do performance testing, but you really have no sense of what the model is about, and you have no good way to interact with it other than, please make a prediction for me. And so I was at NIPS last year, and I went to a bunch of the NIPS workshops, and there was kind of a running theme where people wanted their learning automated. So there was a bunch of workshops like AI for data science and Bayesian parameter optimization, where people were talking about trying to automate away this drudgery that I was talking about before, the parameter selection, the algorithm selection, the various pre-processing steps, trying to make all that go away. So this is obviously a thing that people want. But it also seems like they want to interact with the process. So there was a bunch of work on deep learning visualizations, the future of interactive machine learning, interpreting machine learning. This is becoming a hotter and hotter topic. So it seems like these two goals are kind of at odds, right? People want automated learning. They want to do machine learning without any sort of technical work or drudgery, but they also want to do some work. They want to interact with it. They want to know what their model is doing. They want to be able to validate, and so on and so forth. So here's a good example from the Bayesian optimization workshop that I was just talking about. Basically, if you don't know about Bayesian parameter optimization, it allows you to tune the parameters for any process that happens to have parameters. So basically, you do an experiment, you pick some random parameters, and then you do that a few times, and then you start to get an idea of what parameters matter using machine learning. And so usually they use a Gaussian process model to kind of estimate the effect of the parameters on the results of the experiment. And then the Gaussian process model tells you which experiment to select next. So gradually, you kind of work your way experiment by experiment to an optimal set of parameters. Optimal-ish set of parameters. And the classic case here is deep learning. In deep learning, they've already used this for a number of years because, again, in deep learning, there's so many parameters, the structure and the learning rate and the gradient descent algorithm and so on and so forth. So this guy was applying, the guy who was giving this particular talk was applying this Bayesian parameter optimization through a bunch of things in a bunch of ways at Twitter. And in particular, he talked about how they had a Hadoop cluster that had to run these big text processing jobs every night, and they wanted to optimize the behavior of this cluster. And so there's a bunch of parameters you could parallelize to some degree and use different servers and so on and so forth. And so he said, oh, this is a great candidate for parameter optimization, except again, the engineers of the cluster didn't trust it. They were immediately asking him, well, what are the really important parameters? And the Gaussian process, there's no really natural way to get at that. So he had to kind of hack importance metrics for the parameters so the engineers would trust the process. He found it difficult to elicit objective functions. So one example was, what was it exactly? So he had, originally they said, oh, we want to minimize the failures for these jobs. And so basically the optimization process said, well, just use the most reliable machine, which of course makes everything take forever because it all has to go through this one machine. And they're, oh, no. We don't want failure at the expense of speed. We want fault tolerance, and we want it to be fast. And so you iterate like this, and the process comes back with a solution. Oh, no, that's not quite right because we specified the objective wrong in some way. And of course, if there's any way to cheat this objective, the system will find it. And so what do I mean exactly by another case of that happening? Another case of, here's a case where people specified an objective function and the system cheated and optimized that objective in a way that the user wasn't expecting. So just to put a finer point on it, there was another workshop, Interactive Machine Learning, where they were talking about exactly this problem. And so they had a reinforcement learning system that was designed to learn how to tutor children in math. And so they had a variety of math subjects, fractions, algebra, all the way up to trigonometry. And it had a variety of little tutorial modules. So you could tell the children, go do these exercises, or watch this video, or play with this interactive animation. And basically, it would use reinforcement learning to figure out what order you should put those modules in, and how often you should show them, if you should go back to a module after a different module, and so on and so forth. So it's basically designing a curriculum, right, for these children based on these little tutorial modules. And so optimality, the feedback signal for the reinforcement learning algorithm, was basically every once in a while they test the children to see how well they understood, and that would provide feedback for the process. So what happens when you have a subject where you don't have a good teaching module for it, right? So let's say in trigonometry is really difficult. All of the teaching modules fail to improve the scores of the students. What do you think the system will do? Does anybody have an idea? That's a good guess. It's not quite what happened, but yes, something like that. What actually happens is that the system decides not to teach trigonometry. Because like, why would it teach it if it can't improve the student's scores, right? Why would it bother with this? It can improve it doing something else. But of course, the curriculum, the need to teach trigonometry is not a option, right? It's a constraint on the sort of solution you can provide. So this is different, right? Like, we said people, humans said, we want you to optimize the scores for these students. Well, you didn't say you had to teach trigonometry, and so it cheats. It tries its best to optimize exactly what you're telling it to optimize. So the other example, this is an actual client at BigML where we had this happen. We had a model to detect fraudulent loan applications. So basically, you'd have some pipeline of loan applications would come in. Some of them were fraudulent. They were fraudsters just trying to get the money and not pay. And you have an army of human underwriters who are analyzing these applications and deciding who to give the money to. And so ideally, you'd like to, of course, reduce the workload of your human underwriters. And so you kind of open up the pipeline to the human underwriters, you have them underwrite for a while, and then you train a model that mimics the human underwriters, right? And so you aggressively try to pass the loans that the human underwriters will also pass and fail the loans that they would also fail. And you're kind of aggressively trying to pass the ones that will pass because there's this next layer, right? You've got this cascade of models. And so, of course, you want to be kind of generous in who you pass because the humans will catch your mistakes, right? So which applications is the system going to learn how to pass? The legitimate ones, of course, because the human operators are passing legitimate ones. But what other applications is the system going to pass? Yes.
Ones that humans wouldn't
yes.
are from.
Yes, exactly. Why didn't we hire you in the first place? Yes. In fact, if you're very good at fraud and you never get caught by the humans, the system will aggressively try to pass you, right? So not only have we, trained a system that has this error, but it's like aggressively trying to break itself all the time. And so this is a case where this is different from a mislabeled point, right? Mislabeled data points, this is, we really knew what the class was, but we put the wrong label on it. No, that's different from what's here. What's here is we put exactly the label on it that we meant to, right? We meant to say a human's going to pass this point. That's not an error in labeling. That's an error in the semantics of the label. It's an error in the human assignment of the label.
Isn't that an error in your training data? You didn't include any historic data. So if you took the data from loans that had been passed in the past as well and indicated whether or not the humans had been accurate, you would have
Yeah, so this is what you need, right?
included that in your
Yes, you need another layer of verification to see that these people are not fraudsters. The human label is not enough. You're exactly right, yeah. Yeah, so the idea here is that people love, that computers can automate their optimization process, right? Computers, you're not going to question a calculator. You put in a couple of big numbers and you sum them, and you look at the sum, and you're going to trust that calculator, right? It's not that people don't trust computers. They know people know what they're bad at. They know when the computer's doing something it's supposed to do. The reason that people want to interact with these algorithms is that they're suspicious of the results of the optimization. And they very well should be, because humans are so bad generally at specifying objective functions. And computers are very good at optimizing those bad objective functions. Right? And this isn't just like some kind of nuisance issue. This isn't, we got it wrong, we have to go back. Like, if you do it wrong, you can start to break things. And the guy at Twitter talked about this. Like, they had to have some bounds on the parameters they could try. Otherwise, every once in a while, the system would try something that was totally crazy and would like bust that night's bust that night's Hadoop run. And so humans don't mind being in the loop. You just have to put humans in the loop how they like to be in the loop. And so that's kind of my argument against automation, is it basically hides detail. And hiding detail is great, but hiding detail is not the entire answer to how to get machine learning into the hands of non-experts. So the other thing I want to kind of talk about here is the notion of abstractions. So everybody who's a programmer knows about abstractions. Basically, you have some translational layer that hides detail from you, but also provides rich opportunity to interact with the underlying process. So these are the kind of two principles of an abstraction. Is it establishes some nice mode of interacting with a process, and it also hides the remaining detail underneath that you don't need to know about. And of course, programming languages themselves are a canonical example. You have the syntax of the programming language, which allows you to interact with the computer, but it also hides the machine code from you, right? You don't need to see the binary. You don't even need to see the machine operators. You just get to see the syntax you're used to. And so kind of in general, abstractions are the thing that make technology usable. And if you're not, in general, abstractions are the things that make technology usable, right? If you don't have a good way to interact with technology, then you're not going to use it. If you do have a good way, as I'll talk about in a little bit, then you'll almost certainly use it. So the way I like this is just stuff I'm making up. This isn't something I'm getting from a paper or something. This is just how I like to evaluate abstractions. So I can do that just like fancy professors can. So abstractions can be strong or weak, right? So in the sort of compression sense. So abstractions can make the interaction free of a lot of the technical detail or leave a lot of the technical detail in. So strong abstractions would be those that are free of technical detail. And then is the interaction natural and intuitive? So stronger abstractions are those in which the interaction layer is something that's kind of easy for a novice to get their hands on and do what they need to do. And then I like to think about this notion of lossy or lossless. So when you put the abstraction on top of something, is the user able to get the result that they want? So programming languages are a near lossless abstraction because you can do almost anything with a programming language that you can with machine code. And then when they can't, do they have like a graceful failure mode? So for example, in Python, if you don't like the primitives that Python is providing, you can write a C library and import that into Python. So you can always get to the layer below. Wavelet-based image compression is another example of this. If any of you are image compression people, the way some of these wavelet algorithms work is they have like a low resolution of the image that loads first, and then the next thing that comes in is the detail, the edge information for that low resolution, and then the next thing that comes in is the sub-detail, basically. And so your image just improves in resolution as it loads. So right away, you get something good, and then you get the lower layers underneath. And of course, it's easy to do just one thing or the other, right? It's easy to hide details from your user and not provide a good mode of interaction. And similarly, it's good to not hide anything from your user and provide them all of the bells and whistles. It's finding the sweet spot that's the difficult bit. So just to talk about abstractions a little bit, some good abstractions. Driving is like the example that everyone thinks about. When we drive, we don't have to think about transmissions or engines or clutches or carburetors. We just think about a steering wheel and a gas pedal and a brake pedal, and we're done, right? That's a good abstraction. It allows us to do everything we want to do with the technology and frees us from all the technical detail. WYSIWYG editors is kind of a silly example, but if you ever work in LaTeX, you get an idea of what WYSIWYG editors are hiding. All of that formatting stuff, all of that metadata. So that's a pretty good abstraction. So what about Bayesian parameter optimization, like I was just talking about? What about these processes that hide you from the details of algorithm selection and parameter tuning? It does hide some parameters, right? But we're talking about something that hides like 20 or 30 parameters, and it's already fitting millions in the case of a neural network, right? Something with millions of parameters. So it does hide a few parameters from you, but really not that many in the context of the overall process. And then also, there's no prescription for how to interact with a Bayesian parameter optimization process. You can set bounds, I guess, on the parameters that you're trying to tune, but other than that, there's no like obvious way to interact with it, as far as I know. So as an abstraction, I think Bayesian parameter optimization is kind of lossy and weak. But again, I love it anyway. It's exactly good. It's good for what it does, right? It does the thing that it's supposed to do. It's just that thing I don't think makes the technology that much more usable. So I wanted to talk a little bit more about abstractions. So, and the idea here is hopefully to get you thinking about abstractions and ways you can kind of package ML, just kind of hints that might give an idea about how to package ML so that somebody might like to interact with it better, somebody might find it more usable. So one of the key lessons here is that people will meet you halfway. You are not, you, the developer of the technology, are not alone. Your customer is kind of on your side. They're trying to use this thing that you're building. And so there's a lot of case studies here. This is just an anecdote that somebody told me when I was an undergrad, which was forever ago. But they were talking about how in the early days of programming, somebody was trying to come up with a sub n cubed algorithm. It was like matrix factorization or something like this, some kind of canonical n cubed, not matrix factorization, but some kind of canonical n cubed problem. And somebody was trying to come up with something that was faster than that. And the person who did was a person who was using a different programming language where sorting was a primitive. Before that was a thing, right? Before sorting was a primitive in all languages, this allowed somebody to think of, oh, if I just sorted n times, now I've got an n squared log n algorithm, like I've gone sub n cubed. And they only thought about that because the sort primitive was there, right? And so this is if you've ever heard of the Sapir-Whorf hypothesis, has anybody? Come on. Yeah, all right. Yeah, so this is the idea that, if you, depending on the language that you know, you'll think different thoughts, basically. So if you're thinking in English, you'll think different thoughts as if, to if you were thinking in, Spanish, because the languages have certain characteristics that encourage certain patterns of thought. And so this is true of programming languages and things in general as well. People will use the primitives that they're given. So case 2, Google. I'm going to make the case that Google is actually not very good. So why are we all using it? We're all using Google, and people will say, oh, you just type into a box and it tells you exactly what you want to know. And so, so where is this? Yeah, so I type PAPIs into a box here, and it's not telling me what I want to know, right? Like, Los PAPIs, oh wait, here it is. There, I found it. So this was the first thing I tried. I did not know that Google was going to fail on the first thing I tried. But it's 10th down here. But what are we willing to do? We're willing to scroll down. Maybe it's not on the first page. Maybe we're willing to try new search terms. The reason is because the mode of interaction is so natural, right? Google just asks for text and it tries to do the right thing. And people are willing to meet Google halfway about that.
How can it do anything other than give you the most popular responses? This is not as popular as pizza. It might be great, but it's not as popular as pizza. So I think that's a cheap shot.
Well, I mean, it's just the first thing I tried, like I said.
But you said Google's not good because it didn't do what I wanted to do.
Well, of course, I'm trying to make a point in the talk, yeah. I would argue that most people don't want to go to Pappy's Grill in Brooklyn. There's only a few people in Brooklyn, comparatively.
I'll bet there's more people there.
Yeah, not this particular example, but the idea of Google being not good, I lifted from another talk that I saw like 5 years ago. So maybe Google's better. And actually, if I allow it to turn on geolocation, it does figure out that I'm here.
At Pappy's or just at?
In the building, yeah. It puts Pappy's as the top result if I enable geolocation. So if it knows where I am, then it gives me the right thing.
Doesn't it know roughly where you are based on the IP address?
Google's so bad, right? Shouldn't it know? Come on. Yeah.
So it shouldn't be giving you Brooklyn. It should be giving you.
Yeah, I was getting pizza places in Newark. Come on. What's that? Yeah. So this is exactly what I'm saying, is that Google is providing the best thing. And I'm arguing that part of what makes it the best thing is the mode of interaction. Like, I'm sure there's a lot of fancy things you could do with, I don't know, text, if you wanted to roll your own text search or whatever, but Google provides this really easy mode of interaction. Okay, and then the last thing I wanted to talk about was decision trees, and I'm going to argue that they're a little more useful than you think. Why am I going to talk about decision trees? Look, they're all down here, right? They're not very powerful as far as predictive models go. This is several packages in R, Weka, and then scikit-learn, a few different trees in Weka. Like I said, that's not what we're talking about here. So the model itself, when you create a machine learning model, it is an abstraction. And what is an abstraction over? It's an abstraction over the data, right? The model hides the details of the data. It hides the individual points. It provides you with effectively a compressed version of your data set that answers questions for you. So it hides the details and it provides interaction for you. So if we're thinking about it in terms of our abstraction kind of fantasy, then at hiding details is very good, right? Even if you have a massive amount of data, the model compresses it pretty effectively. So it hides all of the details for the data. The interaction, though, is generally somewhat lacking, right? All you can do is ask it for a prediction. With the decision tree interaction, well, so this is part of a little bit of the problem that machine learning is trying to solve, right? Or BigML is trying to solve, is giving you richer interaction with the model. So of course, with the decision tree, it's trivial, right? Because decision trees have this structure that's very visual, and so you can make this nice plot. The reason that I like it is because now, when I do data analysis on BigML, I'll just immediately train a decision tree. And I do that just to see what it gives me. So in this case, this is the diabetes data set that I'm sure everybody knows. But immediately, it tells me that your blood glucose is the most important thing. And then you see your BMI is queried several times in here. So immediately, it tells you, without any work, what diabetes is sort of about. It's not the most powerful predictor. It's not even very good. But at the top levels, it gives you a high-level overview of the data. And furthermore, if there's mistakes in the data, if the objective field is in there twice, if the objective field is there as a feature, right? I'm sure a lot of us have encountered this problem where we accidentally give away the answers in the data. If that happens, you train a decision tree, you see it pretty much right away, right? You have a one-node tree that gives you the right answer. Oh, God, my data is broken. And so providing me, a data scientist, this as a primitive gives me something I can work with and do my job faster. And so kind of to sum up, like the usual way going back to the driving metaphor, the usual way we interact with these models is we as machine learning people will say, hey, we've got this great technology, if we're doing the driving metaphor, oh, we've got this great technology that lets you get from here to there. And somebody says, oh, great, I want to get from here to there. And we say, here. And they go, what the hell is this, right? And you say, oh, no, you just have to attach a steering wheel and a transmission and then axles and wheels. And they're like, no, right? And so part of what I'm arguing is that we have to get to the point where we don't just provide them the engine. Even though the engine is like the most important part of the car, and the car doesn't work at all without the engine, and the engine is what provides the actual motion, finally, that's not what people care about. What people care about is how they're going to interact with that thing. Okay, so you can help. So I've just provided us with a lot of problems, right? Do I have any ideas about solutions? I don't know. If I did have a really good idea, of course, I'd be rolling in cash, but I'm not. And so let's just talk about some vague ideas that I have that might work. So expressing human preferences to algorithms. This is like one place where I feel like we could get better. DSLs are a great tool for this. You have a domain-specific language. It allows the user to naturally specify prior knowledge about the domain in some way. Again, this is very vague. I have no idea what form this would take. We're just talking about ways of eliciting information about the domain from the user. Loss function elicitation. This I don't think gets enough play in the academic literature. When I say loss function elicitation, I mean, like, okay, so the dumbest form of loss function elicitation is this cost matrix, right? You just provide what the cost of the false positive is and what the cost of the false negative is. Way better than nothing, right? Because most times it's not totally symmetric. Most times it's something interesting. But can we do better than that? So there are ways of presenting 2 points at a time to the user and said, would you rather see a mistake on this or a mistake on this? And you do that 10 or 20 or 50 times, and you get an idea of what the user prefers to see mistake-wise. And so there are algorithms that allow you to elicit loss functions from users in this way. And then graceful degradation of the loss function to uncertainty. So most algorithms, when you train a model, you make an assumption about the loss function. Oh, I have no information, so I'm going to assume all mistakes are the same. That seems silly to me. Really, what you should be doing if you're a Bayesian, what you would do is you would say there's a distribution over loss functions, right? And you would get evidence in, and eventually your uncertainty about the loss function would reduce to nothing. And so graceful degradation of your knowledge about the loss function to a completely uncertain state would be interesting. And then model interaction. This is a little more straightforward. Meaningful interactive visualizations. We're working on this, but it's really hard, right? It's really hard to come up with something that's intuitive and that explains what the model is doing in a way that you can see on a browser screen. And then frameworks for question answering. This is something that I've recently gotten interested in. Like, if you're allowed to, interrogate the model a little bit, what does that look like? What do the model's answers look like? So ways you can interact with the model beyond just asking for a prediction, like things like, what if this field is this and this field is this, but everything else we don't know about, and the model can explain how important those things are. Things like that. Something richer than just raw prediction.